This is a companion video for our paper towards modeling and influencing the dynamics of human learning. Humans have internal models of robots, like the robot's physical capabilities, the world, like what will happen next, and their tasks, like a preferred goal. However, human internal models are not always perfect. For example, imagine your first time calibrating a robot arm to follow a desired path. But you are not familiar with the robot's dynamics, so your initial motions are jerky and imprecise. However, your internal models change and improve as you gather more experience. Since the robot is part of the world, the robot's actions and their outcomes become part of your experience. In other words, robot actions inevitably influence a human's internal model. In this work, we take a step towards enabling robots to understand the influence they have, leverage it to better assist people, and help human internal models more quickly align with reality. We model the human with an internal parameter vector theta h, which captures a latent aspect of the task that the human is uncertain about but continuously learns about. For example, this could be the dynamics of the robot, the human's goal, or their task preferences. Similar to prior work, we treat the human as a noisily optimal actor under their internal model parameter. As a human acts in the environment, they receive new observations, such as the next date. This naturally lets the human update their internal model. We can view this learning process as a dynamical system where the human's internal model is a state and the observations evolve their internal model. However, this does not prescribe the precise functional form of how people learn in a way that can be used by the robot. One idea is to draw on computational cognitive science work, which posits that humans learn by approximate Bayesian inference. However, people have been shown to have many cognitive biases, which deviate from perfect Bayesian inference. Instead, we take a robotics perspective and view this challenge as an instance of a general dynamics learning problem. We leverage demonstrations which naturally exhibit human learning to infer an approximate model FLFA. This enables flexibility of capturing different possible learning updates at the cost of being domain-specific. First, we collect state action demonstrations of multiple people learning on their own, like controlling a robot that they have never interacted with before. We want to fit an approximate nonlinear model of the dynamics of human learning at alpha. We want to infer the parameter of the human's learning dynamics phi as the initial human internal model theta 0, which maximizes the likelihood of the demonstrations, assuming that the observed human actions are approximately optimal under their current internal model. Unfortunately, this general problem is computationally intractable because the human is acting under a possibly different internal model at each time step, requiring us to solve for an entirely new human policy at each time step. Our idea is to use a linear quadratic approximation to obtain a closed form expression of human policy at any time step and a differentiable inference objective. Inferring how humans learn presents an opportunity for the robot to influence human internal models. We formalize this as a Markov decision process, where the state contains both the physical state of the world and the human's internal model parameter. The physical state evolves by physics, and the human's internal model evolves by the inferred learning dynamics FLFA. Under this new MDP, the robot optimizes a policy that maximizes its own reward to influence the human's internal model by changing the observation the human sees if it yields a higher reward. We conducted an NLRB-approved user study in shared autonomy settings where the human uses the webcam-based gesture interface to control a robot arm towards 4 goals on the table. In software, we simulated the new robot dynamics that the human had to learn about by biasing the enemy effector to consistently experience lag in one direction. We recruited 12 participants, none of which had experience with the robot. We used a 2x2 factorial design and manipulated the robot strategy, active teaching, where the robot influences the human's internal model, and a passive robot, where the robot does not intervene. We also manipulate the dynamic stack, robot lagging in X direction or Y direction. We used a within subject design and counterbalanced the order of conditions. Although we do not have access to the human's internal model, as a proxy, we measured the distance between the human's executed action and the optimal action under true robot dynamics. Intuitively, the better the human understands the robot, the more optimally they should be able to control it. We have two hypotheses. First, participants in the active teaching condition become optimal calibrators faster than passively learning on their own. Second, participants feel they learned faster and understood the robot dynamics better in the active teaching condition. Here, we show the human's action optimality distance over time and under each robot strategy. We conducted an ANOVA of these results and found a significant main effect of the robot strategy supporting hypothesis 1. Our qualitative results shed more light on this. When the user learns on their own, the execute trajectory is constantly suboptimal, weaving around the optimal path. In contrast, in the active teaching condition, the initial portion of the robot trajectory exhibits robot teaching behavior. We can see that the robot intentionally exaggerates the dynamic bias to change the human's internal model faster. After this initial deviation, the human has a better understanding of the robot's physics, and the later motions are closer to optimal compared to the passive learning trajectory. We further ran an ANOVA on the Likert survey questions, but we did not find a significant effect of the robot strategy, rejecting hypothesis 2. In this work, we take a step towards modeling the dynamics of human learning and influencing through robot actions. In the future, we are excited about more work towards long-term and stable robot influence.